The sun has been a major area of strength for us, particularly of late, and it will go through a critical, also enamoring change, the reversal of its charming field. This attachment happens for the most part at standard reaches, meaning the midpoint of the solar cycle, and it has far-reaching repercussions for us here on Earth. Believe it or not, it's possible that rapidly the sun could present a serious risk that could cause complete disruption and disaster for everyone on the planet. As you will find, the sun's appealing field is created by the movement of electrically charged gases in its interior, a process known as the solar dynamo. Over the long haul, this appealing field becomes increasingly heavenly and reshaped due to the sun's transformation and convective changes. Eventually, this cycle leads to a complete reversal of the magnetic poles. The north magnetic pole changes into the south magnetic pole and vice versa. So, could we break down the whole cycle and take a more gathered look at the sun? The sun is made primarily out of hydrogen and helium as plasma, a state of matter where electrons are not bound to particles, resulting in a mixture of free electrons and ions. The sun's interior is divided into several layers, with the center at the middle, encased by the radiative zone and the convective zone. The center is the sun's most significant area, where nuclear fusion occurs, converting hydrogen into helium and releasing enormous amounts of energy. Above the core lies the radiative zone, where energy is transferred outward via radiation. In this area, energy moves slowly outward as photons are absorbed and re-emitted by the solar plasma. The outer layer of the sun's interior is the convective zone, where energy is transported by convection. Hot plasma rises toward the surface, cools, and sinks again, creating convective currents. The solar dynamo process works fundamentally in the convective zone and the tachocline, a thin layer that lies between the radiative zone and the convective zone. The tachocline is critical because it's where the sun's differential rotation and shear flows play an essential role in creating the magnetic field. Now, here's something interesting that you probably haven't heard. The sun doesn't rotate as a solid body. Rather, different parts of the sun rotate at different rates, with the equator rotating faster than the poles, a phenomenon known as differential rotation. This differential rotation stretches and twists the magnetic field lines, elongating the magnetic field. The solar cycle is an approximately 11-year cycle during which the sun's magnetic field undergoes a series of changes, culminating in a reversal of its poles. This cycle is driven by the solar dynamo and involves several stages. At the beginning of the solar cycle, the sun is in a state known as solar minimum, characterized by a low number of sunspots and minimal solar activity. The magnetic field is generally simple and bipolar, with a clear north and south magnetic pole. As the cycle progresses, the number of sunspots increases. Sunspots are regions of intense magnetic activity and are associated with the rise of magnetic activity from the sun's interior. These sunspots appear in pairs with opposite magnetic polarities and migrate toward the equator over time. Around the midpoint of the solar cycle, the sun reaches solar maximum, a period of peak activity, with the greatest number of sunspots, solar flares, and coronal mass ejections, CMEs. The magnetic field becomes extremely complex and tangled due to the continuous twisting and shearing by differential rotation and convection. As solar maximum fades, the magnetic field begins to reconfigure itself. The reshaped and tangled magnetic field lines reconnect, and the global magnetic field gradually reverses its polarity. The north magnetic pole becomes the south magnetic pole and vice versa. This cycle is facilitated by the advance and restructuring of solar plasma movement regions. After the pole reversal, the sun enters a period of declining activity, returning to solar minimum. Eventually, the magnetic field reconfigures, and the cycle is ready to begin anew. At present, we're in the solar maximum stage, and the sun's magnetic field is about to flip. During this stage, we can expect to see some activity from the sun that could be as dangerous as it is captivating. However, the sun's magnetic field reversal is not an unexpected flip, but rather a continuous cycle. As the solar cycle advances, the sun's magnetic field undergoes a series of changes. At the moment the magnetic field is at its most twisted and tangled state, it reaches a tipping point and begins to reorganize itself, resulting in a flip. So, do we know when the sun's magnetic field will flip? Scientists monitor the sun's magnetic activity using various instruments and techniques. Observatories equipped with powerful telescopes, both on Earth and in space, provide detailed images of the sun's surface and its sunspots. Instruments like the Solar and Heliospheric Observatory and the Solar Dynamics Observatory measure the sun's magnetic field and its changes over time. One key indicator of an impending magnetic reversal is the behavior of sunspots during solar maximum. Sunspots appear more frequently and become more pronounced as they move toward the sun's equator, a sign that the magnetic field is becoming more unstable and is preparing to flip. While we're on the subject, let's dive a little deeper into sunspots. When the sun's magnetic field lines become twisted and tangled due to differential rotation, the sun's equator rotates faster than its poles, causing the magnetic lines to stretch and bend. When these lines loop over the sun's surface, they suppress the convective movement of hot plasma from the sun's interior, resulting in the cooler, darker patches we see in sunspot images. Sunspots are not only fascinating solar features, but they can sometimes produce powerful solar flares and coronal mass ejections, CMEs. These phenomena release vast amounts of energy and charged particles into space. When directed toward Earth, they can disrupt satellite communications, affect power grids, and pose threats to astronauts in space. Moreover, increased solar activity can enhance auroras, but it can also raise radiation levels in Earth's upper atmosphere. So while we're on the topic, let's examine the difference between solar flares and coronal mass ejections, CMEs. While both are massive outbursts of energy from the sun, they differ significantly. Solar flares are sudden, intense bursts of radiation caused by the release of magnetic energy associated with sunspots. They release a tremendous amount of energy and light, often in the form of X-rays and ultraviolet radiation. Think of them as bursts of bright light and heat on the sun's surface, like a large explosion. In contrast, CMEs are enormous releases of solar wind and magnetic fields from the solar corona. They can be thought of as giant bubbles of gas and magnetic fields being expelled into space. When a coronal mass ejection occurs, it sends billions of tons of solar particles into space at extremely high speeds. So while solar flares and CMEs are related, they are not the same. A solar flare can occur independently, but sometimes an exceptionally powerful solar flare can be accompanied by a CME. Although a solar flare doesn't necessarily cause a CME, they can be linked in terms of risk. Solar flares can disrupt radio communications, navigation signals, and pose a significant risk to astronauts in space due to the intense radiation. However, CMEs can have a broader impact. CMEs can cause geomagnetic storms that disrupt power grids, satellite operations, and navigation systems. They can also enhance auroras but pose serious risks to Earth's technology and infrastructure. Another consideration is that during times of high solar activity, the amount of high radiation reaching Earth also increases. Satellites and other space vehicles are especially vulnerable to elevated solar activity. The charged particles from the sun can damage electronic components, disrupt communication signals, and even alter satellite orbits. Beyond causing harm to technology and infrastructure, what else can happen to the planet? While the sun's magnetic field reversal doesn't directly impact Earth's atmosphere, the related changes in solar activity can have an effect. Some studies suggest that variations in solar radiation can influence atmospheric conditions and weather patterns. For example, increased solar activity can lead to a slight warming of Earth's atmosphere, potentially fueling existing climate change. Might auroras be the only positive aspect we experience here on Earth? Perhaps one of the most striking effects of increased solar activity is the enhancement of these spectacular lights. These natural light shows, known as the northern and southern lights, occur when charged particles from the sun interact with Earth's magnetic field and atmosphere. We often hear about the aurora borealis, but these lights can also be seen around the South Pole during times of high solar activity. Auroras become more frequent and can be visible at lower latitudes, offering dramatic evening displays. However, besides the beautiful auroras, there are also more concerning aspects of the sun's magnetic reversal that could occur if we are unprepared. One of the primary threats associated with a magnetic field reversal is the increased likelihood of geomagnetic storms. These storms occur when solar wind, overloaded with charged particles, interacts with Earth's magnetic field. In extreme cases, they can cause widespread blackouts and damage infrastructure. One such event occurred on the morning of September 1, 1859. Astronomer Richard Carrington was observing the sun through his telescope, as he had done many times before. However, what he saw on this particular day would stand out in history as the first recorded solar storm. At 11:18 a.m., Carrington saw a bright flare of white light emanating from a group of sunspots. This event, now known as the Carrington event, marked the beginning of the largest geomagnetic storm ever recorded. The white light Carrington saw was an enormous solar flare, an intense burst of radiation caused by the release of magnetic energy stored in the sun's environment. This flare was so powerful that it triggered a massive coronal mass ejection, CME, directed towards Earth. The CME reached Earth in just 17.6 hours, a remarkably short time, considering the sun is 93 million miles away. When the CME hit Earth's magnetosphere, it triggered an exceptionally strong geomagnetic storm. The impact was quick and widespread, disturbing Earth's magnetic field and inducing currents in the ground. Furthermore, telegraph lines, which were the backbone of global communication at the time, experienced severe disturbances. Sparks flew from telegraph machines, operators received electric shocks, and some message stations even burst into flames. The induced currents were so strong that operators could send and receive messages even after disconnecting their batteries. One of the most striking and noticeable effects of the Carrington event was the brilliant display of auroras. The auroras were so bright and widespread that they were visible far beyond the typical polar regions. People as far south as the Caribbean, Mexico, and Hawaii reported seeing the sky illuminated with vibrant colors. The auroras were so intense that they lit up the night sky, allowing people in the northeastern U.S. to read newspapers by their light. In the Rocky Mountains, gold miners were reportedly awakened by the brightness, mistaking it for sunrise and beginning to prepare breakfast. People described the sky as having glowing red, green, and purple hues moving and shimmering across the horizon. Now, imagine if a solar storm of the magnitude of the Carrington event were to hit Earth today. The consequences would be catastrophic. The sun is undergoing a massive transformation, the reversal of its magnetic field, a process that happens roughly every 11 years as part of the solar cycle. This event, driven by the solar dynamo, could have far-reaching consequences for Earth, potentially causing disruption and disaster. The sun's magnetic field is generated by the movement of electrically charged gases in its interior, creating a complex magnetic field that eventually reverses its polarity. The sun is primarily made of hydrogen and helium plasma, with energy produced by nuclear fusion in its core. This energy is transferred outward through the radiative zone and then by convection in the outer layers. The solar dynamo system, which operates in the convective zone and the tachocline, generates the sun's magnetic field. Differential rotation of the sun, where the equator rotates faster than the poles, stretches and amplifies the magnetic field lines, driving the solar cycle. At present, the sun is in the solar maximum stage, where sunspots and solar activity are at their peak, potentially causing risks like solar flares and CMEs that can disrupt satellite communications, power grids, and pose threats to astronauts. Scientists monitor the sun's magnetic activity and sunspot behavior to predict when magnetic field reversals will occur. Sunspots, which result from tangled magnetic lines, can produce solar flares and CMEs, both massive releases of energy that affect Earth in various ways. While solar flares emit radiation, CMEs eject vast amounts of solar particles into space. These phenomena can enhance auroras but also pose critical risks to Earth's technology and infrastructure. The sun's behavior is a fascinating interplay of physics and natural phenomena, affecting not only our solar system but also life on Earth. Understanding the complexities of solar activity is crucial, especially as we continue to rely on technology that can be impacted by solar events. The sun generates energy through nuclear fusion, converting hydrogen into helium and producing enormous amounts of energy in the process. This energy travels through the various layers of the sun, eventually reaching the surface and radiating into space. Solar activity can manifest in many forms, including sunspots, solar flares, and coronal mass ejections. Sunspots are cooler areas on the sun's surface caused by magnetic activity, appearing as dark spots. These changes in solar activity follow an approximately 11-year cycle known as the solar cycle, where periods of high activity, solar maximum, are followed by calmer periods, solar minimum. During solar maximum, the number of sunspots increases, leading to more frequent solar flares and CMEs. Solar flares are sudden outbursts of energy that release radiation across the electromagnetic spectrum, including X-rays and ultraviolet light. These intense bursts can affect radio communications and pose risks to astronauts in space. CMEs, on the other hand, are enormous eruptions of solar wind and magnetic fields that rise from the solar corona and are released into space. When directed toward Earth, these ejections can cause geomagnetic storms that disrupt the planet's magnetic field, leading to beautiful auroras but also potential interruptions to technology. The effects of solar activity extend beyond space. They influence Earth's atmosphere and surface. Studies suggest that variations in solar radiation can affect climate patterns, potentially contributing to weather anomalies. Increased solar activity can also lead to atmospheric warming, which is an important factor in discussions about climate change. Additionally, the potential for technological disruption due to solar storms cannot be understated. A severe geomagnetic storm could damage electrical grids, disrupt satellite operations, and affect navigation systems. Preparing for such events involves monitoring solar activity and developing strategies to mitigate their impact on infrastructure. Researchers continue to study the sun's magnetic field and its cycles to better predict when significant solar events may occur. This research involves a combination of ground-based and space-based observatories that track sunspots, measure magnetic fields, and analyze solar wind. With advancing technology, our ability to predict solar activity improves, which is essential for protecting our technological systems and ensuring the safety of astronauts as we explore space. As we study the sun, its impact on Earth becomes increasingly clear. From the stunning displays of auroras to the potential challenges posed by solar storms, the sun remains a powerful force in our solar system. Understanding its cycles and behaviors not only advances our knowledge of space science, but also enhances our preparedness for the impacts of solar activity on modern life.